So in this video, I wanted to add a clarification to the previous video that I posted. The previous video, I think, did a very, very good job of explaining the difference between how ionic compounds dissolve in water versus how covalent compounds dissolve in water. However, one thing I noticed about that the video is that it assumed that the ionic compound that you are going to be using was comprised only of monatomic ions, all right? And recall from our unit on ionic compounds that the ions in ionic compounds can either be monatomic ions, where the ion is a single atom having a charge. For example, when you have sodium chloride, this is an ionic compound made up of two monatomic ions. You've got a positively charged sodium atom, and you've got a negatively charged chloride atom, all right? But there's also ionic compounds where you have polyatomic ions, all right? An example of this, something like sodium cyanide, all right? Where the positive thing in this ionic compound is a positively charged sodium atom, but the negative thing is a polyatomic ion, cyanide. It's these two atoms together, which, excuse me, these two atoms are covalently bound, but together they have a negative charge. All right, so cyanide this would be an example of an ionic compound where one of the ions is a monatomic ion and one is a polyatomic ions. All right, and so I wanted to give a little clarification on how these two different types of compounds, two different types of ionic compounds would dissolve. All right, so when you have an ionic compound where both of the ions are monatomic, it happens exactly the way it was described in the video. All right, so for example, sodium chloride, when you dissolve that in water, and I'm just using these blue stripes here as pure water, what would happen? So this would be like a crystal of sodium chloride. The atoms would separate from each other. All right, that's called dissociation. All right, the thing that's always true is to say that the ions separate from each other. All right. I like that term better than saying that the atoms separate from each other, because that's not always true. All right, so let's contrast that with when you have an ionic compound that contains polyatomic ions. All right, so for example, sodium cyanide. All right, if you were to have a crystal of sodium cyanide, your arrangement of atoms might be something like this. Notice that you've got your positive one charge something, you've got your negative one charge something. It's just that this is a monatomic positively charged something. This is a polyatomic negative one charge something. All right, so this would be like a crystal of sodium cyanide. And when that dissolves, notice that the ions separate from each other. It's just that one of those ions is a polyatomic ion. And when those separate from the other ions, notice that the atoms within that polyatomic ion stay connected to each other. So the carbon is covalently bound to the nitrogen, but together those things overall have a negative one charge. All right, so that is the cyanide polyatomic ion. All right, so notice that there's, when this thing right here separates, all right, a way that we could represent it as an equation is to show that this atom right here separates, but these two atoms stay together. All right. When you have the AQ, that just means aqueous, all right, which means dissolved in water, all right? So I could do this for a couple different examples, but there's I'm going to try to show the 4 possible combinations of this, all right? And then instead of showing this as a cartoon, I'm just going to show it as an equation here, all right? So if you had a compound where all of the ions were monatomic ions, all right, so you've got a calcium +2, and then you've got 2 Br minuses, all right. If that were to dissolve, all of these ions break apart, all right. So I just said 2 Br minus. You could have shown this as plus Br minus plus another Br minus, but notice all of the atoms, in this case, all of the atoms break apart because each of the ions is an individual atom, all right? In this case, we have ammonium chloride, all right? This is a case where the positive ion in this is a polyatomic ion, which is right here, And the negative ion is a monatomic ion. All right, so notice when these dissolve, the ions break apart, but one of the ions is this polyatomic ion, and notice that the atoms within that polyatomic ion stay connected. All right, here we've got the opposite. This is sodium sulfate. Notice that the monatomic ions, the positive thing are monatomic ions. You've got two of those Na plus ions, but your negative ion is a polyatomic ion. That's sulfate right there. All right, and so when that breaks apart, you generate two of those monatomic ions. All right, and you also generate one of the sulfates, but notice that the oxygens and the sulfurs within that polyatomic ion stay connected. All right, the last combination would be if both your positive and your negative ion were polyatomic ions. All right, so an example of that would be ammonium cyanide. All right, where this is your ammonium group that's got a +1 charge. This is your cyanide, which has got a -1 charge. And when that breaks apart, you're going to generate one of each of those. All right, so key thing to remember about this is what happens when something dissolves in water. All right, remember we're going to talk about solubility rules when sometimes these ionic compounds don't dissolve in water. And so there are cases, all of the examples that I showed here show cases where the particular ionic compound would dissolve. All right, so next thing that you're going to be watching is the solubility rules that describes how to predict whether or not it would dissolve.